Hello, it's Paul with some graphical examples of continuity and uniform continuity. Let me set up as much space as I can get on the screen and set up a couple of axes and define a function, x to the 3/2 power. What we want to do is to show that this function is continuous at the point x equals 2. And I'm going to do this using two alternative definitions. I'm going to start with the one from Ross, which is probably not one that you learned in a previous course. I call it the no bad sequence approach, and this is going to turn out to be very useful when we do continuity not in R but in Rn. This definition requires a couple of sequences. First, a sequence in the domain that converges to 2. So I will take 2 and subtract off 1 over n to the 1.1 power. This leads to a nice looking display. And there's the sequence shown on the x-axis. The first term is 1, and it's clear the points in that sequence have a limit of 2. Now I can apply my function to that to get a sequence of function values. They will be in the codomain, of course. And when I plot those in red and display them on the vertical axis, it's obvious that that sequence converges to f of 2. We'll call this sort of sequence a good sequence. It converges to a certain point in the domain, and in the codomain it converges to the function value at that point. So Ross's definition of continuous is that there are no bad sequences. Every sequence is good if the sequence in the domain converges to 2, the sequence of function values in the codomain converges to f of 2. Here's an alternative definition using epsilons and deltas. We pick an epsilon, like 1/2, and we use it to set up a target band above and below f of 2. Now the challenge is to find a delta in the domain that meets this target. So by looking at the graph, I decided delta of 0.2 seemed to do the job, and if I look at the interval in the domain between 2 minus delta and 2 plus delta, in between the blue lines, you can see that if I choose a value in the domain between the two blue lines, I get a value in the codomain between the two red lines. It's a provable theorem that this definition is equivalent to the no bad sequence definition. Of course, here the idea is it has to work for any epsilon greater than 0. If I choose a smaller epsilon, as represented by the dashed red lines, I need a smaller delta, as represented by the dashed blue lines. And using this definition, the way to do a formal proof of continuity is to invent the function that, given an epsilon, chooses an appropriately small delta. Now let's see what happens if our function is discontinuous. So I'll redo the plot, redo the axes, and then by adding on the function x greater than 2, which is 0 when it's false, x is less than or equal to 2, and 1 when it's true, I create a nice looking discontinuous function. Now I can construct a bad sequence. I'll start with my same old sequence in the domain, except this time I'm going to creep down on the value 2 from above. Now let's compute the function values in the codomain and plot those, and you can see that it doesn't converge to f of 2. F of 2 is a little bit less than 3. Since all these points are greater than 2, we always get function values above 3.8 or so. So this is a bad sequence, and the existence of this one bad sequence is sufficient to show that the function is discontinuous. Let's go from bad to worse. I can make an even worse sequence by slapping on a -1 to the n, so that now my sequence in the domain alternates between values that are less than 2 and values that are greater than 2. When I get the corresponding values in the codomain, some of them are less than 2.8, others of them are greater than 3.8, and the sequence in the codomain not only converges to a different value, not only fails to converge to the value f of 2, it doesn't converge to anything at all. It's a really bad sequence. We can do the same thing using epsilon and delta. I choose an epsilon. I set up a band around the function value at 2. And since I chose epsilon to be smaller than the discontinuity in the function, there's no delta that can possibly meet this target, because no matter how small a delta I pick, if I go to the right of x equals 2 in the domain, the value in the codomain is going to lie outside the epsilon band above the top red line. Now let's look briefly at the concept of uniform continuity. I'll use the same function, except my challenge now will be to show that it's uniformly continuous on 0 to 4. For proving continuity, we started by agreeing on x equals 2. For proving uniform continuity, we choose our epsilon first. So I'll choose epsilon equal to 0.5. And now I can put the epsilon band anywhere I like in the codomain. I can put it down near 1. I can put it higher up. I can put it higher up yet. And to prove uniform continuity, I have to find a delta that does the job no matter where I place the epsilon band. So here's an example of one that isn't good enough. Delta equals 0.28. If I set up a delta band down around 1, I just barely make it. Get in between the blue lines in the domain. The values in the codomain are between the red lines. But if I move this up near 3, it's very clear that there are points in the domain that lie in between the blue vertical lines where the function values lie outside the epsilon band. However, in this case, since the function really is uniformly continuous, all I have to do is choose a smaller delta. This one works even better near 1, but it also works satisfactorily near x equals 3. Well, I'm not sure about that. I think I should have made it a little bit smaller. So the general rule is, if you have a function that's continuous on a closed and bounded interval, it's also uniformly continuous. Let's see what can go wrong. Things can go wrong only if the interval either fails to be closed or fails to be bounded, because we're going to be able to prove that continuous on a closed bounded interval means uniformly continuous. So here is a function that is continuous on the open interval from 0 to 2. This interval does not include the point 2, because if I substitute x equals 2 into this function, I'm dividing by 0. I plot the function, and it rises rather abruptly as x approaches 2. Take what looks like an easy challenge. Epsilon is equal to 1. But if I place this band up very close to the maximum value of the function shown on the screen, you can visualize that putting two vertical lines so close together that the function values lie between the red lines is beyond the limits of resolution of the plotting that we can do in R. So that's what can go wrong if the interval is not closed. If it's not bounded, something similar happens. Here is the function x cubed over 100. When I plot that, you can see the derivative keeps getting bigger and bigger. Epsilon of 30 looks like an easy challenge, but if you place it near the right-hand edge, again, I'd need an exceptionally small delta in order to get the function values in between those two red lines, which have in fact merged with one another. And while I can't show this on any plot of finite size, I can always place the band in such a way that the derivative is arbitrarily large, and that's why no delta ultimately will work. Since the problem is that the derivative is unbounded, you might already have conjectured that there's a theorem that says if the derivative is bounded, that's also good enough for uniform continuity, and we'll prove that one too.